for Thursday's lab. The instructor here, Matt Shimadzu, he'll be subbing for me Thursday lab. I don't have a sub yet for tomorrow. I'm not tomorrow, Wednesday, and so I'll know by tomorrow. I might have to cancel class, which I'll see. Hopefully not. Yeah, sorry. All right, today what I'm going to do, I'm going to jump ahead a little bit. I'm going to jump ahead and talk about chemical properties. That way, when we're going through all these compounds, we can start to learn some of the chemical properties of them, rather than just naming them or working out problems without really understanding any of the properties. Yeah, like I said, tomorrow I'll know. I'll also post it on Piazza. Chemical properties or reactions. If you think about all the chemical reactions that occur in nature, there's a huge number of chemical reactions. You know, I mean, it would just be hard to count. So many different reactions or processes happening. And so what we want to do is we want to see, are there any patterns in chemical reactivity? We're in the supplement. It's not even in the textbook. It's in the textbook, but it's all, the textbook has it organized differently. And since I want to start talking about it now, but even the supplement has it organized differently than what I'm going to talk about. I think the supplement, you know, if you look at the patterns in chemical reactivity, the supplement has about 12 or more patterns in chemical reactivity, so you start memorizing it. If you take this with this, you get this, right? And I'm not into that kind of pattern. You know, I don't like this. You know, it's like if it falls outside the pattern, then you can't really say much about it. But I have a different kind of pattern, a more loosely defined pattern. And so when I look at patterns in chemical reactivity, I only see three main types of patterns, three main patterns in chemical reactivity. And so if you take, you know, thousands upon thousands of chemical reactions that just take place around you, let's see, three. Now this is where I'm going to be dramatically different than your book, as well as the supplement. So three types, three main types. And so we'll discuss each of these in a lot more detail, but let me just give you the rundown right now. The first type of reaction is something called a metathesis reaction. A metathesis reaction, you see an example of that. Maybe it's easiest. Let's take this compound here. You know what this is called? Actually, let's not take this one. Let's take this one. We call this aqueous. That's what the AQ refers to. Aqueous, what? AgNO3. AgNO3 is called silver nitrate. Or is it silver 1 nitrate or just silver nitrate? Would we use a Roman numeral with silver? No, because we know it's fixed charge. Would we call it monosilver, mononitrate? No, because it's not a binary molecular comment. So this is aqueous silver nitrate. Aqueous just means dissolved in water. This stuff does dissolve in water. We could have that. And then if we mix this with this, minus HCl, which is called hydrochloric acid. Hydrochloric acid is one of the most common, if not the most common acid in lab, hydrochloric acid. What happens is that these two chemicals react with each other, and when they react, all we do is swap the ions. So if we swap the ions, then we'll put the silver cation with the chloride anion, and then the hydrogen cation with the nitrate anion. So we end up with this, just swap. In other words, we're just going to switch partners here. And when we switch partners, it turns out that silver really likes chloride. And what happens is it forms a solid. This solid we call a precipitate. And the precipitate of silver chloride is a lattice structure, extended lattice structure. So the ions come together and form this lattice, or crystals. The nitric acid is just AQ, it just stays dissolved in water. So this precipitate is very favorable. This would be an example of a metathesis reaction. It's just switching ions. I like to think of metathesis as favorable ion combinations. When we look at, ion partners, which ones are especially favorable. Well, ones that form precipitates are very favorable. The precipitates are insoluble, that is, they don't dissolve in water. So something like silver chloride will come out of the water once the second type of reaction is an acid-base. And we look at just one type of acid-base reaction, which is called the Bronsted acid-base reaction. Okay, so metathesis are favorable ion combinations. Bronsted acid-base reactions are what we call proton transfer reactions. That is, the H plus is transferred. And so the acid we call a H plus donor. The base is an H plus acceptor. And so we can easily recognize an acid has to have hydrogen as a cation. I mentioned this before. And so we could have HA. This would be called a monoprotic acid because it just has one hydrogen ion or one proton. A is just a generic term for anion. We could have H2A, which would have two hydrogens for every anion, or H3A. We could also have acid anions like HA minus, etc. And so these are all acids because they all have the H plus cation, and the H plus cation can be transferred in a reaction. So this is called proton transfer. This one's favorable ion combinations. How do you know which ones are favorable? We'll learn them. Favorable ion combinations. All right, the third type of reaction is what we call redox. Redox. Redox stands for oxidation, reduction. Oxidation, reduction. And so, an example of a redox reaction would be something like sodium solid. Is that sodium ion? No, it's not sodium ion because there's no charge here. This is just sodium, the element, which we call sodium metal. Plus chlorine. We'll take chlorine, Cl2 gas, which is also elemental chlorine. And from this, we're going to form sodium chloride. So if we take some sodium, react it with some chlorine, we'll form sodium chloride. But sodium chloride consists of the ions, not the neutral elements. In other words, I have sodium metal here, but I don't have sodium metal here. What happens is this. I have my sodium metal, and what that must do is it must lose an electron to form sodium ion. And the electron has to be going somewhere. In fact, the electron is taken away from sodium. It's taken away from sodium by something else. it's taken away from sodium by chlorine. And so what we'll do here is we're going to dissociate the chlorine. That is, we're going to break the chlorine-chlorine bond and make two atoms. And then one of these atoms of chlorine will take that electron to form chloride. And so basically we're going to end up with a sodium ion, which is positive, and the chloride ion, which is negative here, from the neutrals. Now we have to balance out the atoms, because atoms can be either created or destroyed, so we'll need two of these on my solid sodium chloride. And so what we say for this top one is that sodium was oxidized. Oxidized means it lost electrons. Sodium was oxidized, lost electrons. Just one electron. So sodium was oxidized, but who oxidized sodium? Where did that electron go? Yeah, to chlorine, which forms chloride. So sodium was oxidized, lost an electron by chlorine. Chlorine is called the oxidizer. The oxidizer, we're going to use another name for that. We're going to call it the oxidizing agent sometimes. Oxidizing agent. And so sodium was oxidized by the oxidizer, chlorine. Or sodium was oxidized by the oxidizing agent, chlorine. So chlorine is the species responsible for doing the oxidation. Here, what we say here is that chlorine itself, chlorine was reduced. Reduced means gain electrons. Chlorine was reduced. That is, it gained electrons. Who reduced it? The sodium reduced it. This is where the electron originated from. So chlorine was reduced by the reducing agent. Sodium, which is a reducer. Sodium is a reducer. So that's a little bit of it's a little bit tricky. There's something called oil rig. Have you heard of oil rig? Maybe not. Oil rig. Oil stands for oxidation is loss of electrons. Rig is reduction is gain. And so here sodium is losing electrons. We'll call that oxidation here on the top. But sodium is undergoing oxidation, but sodium itself is not the oxidizer. Some other species is causing the oxidation. Occur that the species is chlorine. Chlorine is the oxidizing agent, but it's undergoing reduction. So rig, reduction is gain, oxidation is loss. So we're going to get more familiar with these terms. And so one way of thinking about a redox reaction is this is electron transfer. So the reason I'm introducing it early is because if we're going to practice nomenclature, naming these compounds and whatnot, we might as well learn a little bit about their chemistry along the way. That way you have more time to absorb these things. So as far as metathesis properties go, we want a driving force. So what are good favorable ion combinations? So let's go back to metathesis a little bit. For metathesis, we want to memorize the solubility rules. So we you want to start doing that as soon as possible. Start memorizing the solubility rules because these will come in quite handy as we go on. So every compound we're going to look at in terms of solubility. So the solubility rules, we break them up into two parts. One, we have the solubility rules for molecular compounds. For molecular compounds, we have things like this. The rule is very simple. It's like dissolves like. Like dissolves like. That's it. So an example of this would be sugar. Sugar and water. Sugar and water. Does sugar dissolve in water? Well, it doesn't seem like sugar is very much like water, but it turns out it is in certain ways. It is in terms of something we call polarity, which I'm going to talk about when we get to structures. But sugar is polar, water is polar, and so sugar dissolves. And therefore we say it's soluble. However, if we have something like oil and water, does oil dissolve in water? No, because oil is quite unlike water. Oil is what we call nonpolar. Nonpolar. Water is polar, and so it's not soluble. Not soluble we call insoluble. And so there are different ways of looking at solubility. And so note, qualitative versus quantitative. We're going to be looking at things quite qualitatively, so this will just be a little sidebar here. But qualitative measures are like this. Qualitative, we break things down into soluble, S. Soluble just means a decent amount will dissolve, maybe not all of it, you know. So for example, is there a limit to how many sugar cubes you can put in coffee, or is it unlimited? Can you put an infinite number of sugar? I want the sweetest coffee in the world. Is it possible to put an infinite number of sugar? No, eventually what's going to happen? It's going to stop dissolving, but it'll get plenty sweet. You know, you'll saturate, what we call saturate your coffee with sugar. Probably taste, maybe it'll taste good, maybe it'll taste awful, but we could get it saturated. That won't be. And so certain things will have a limit, but just as long as we can dissolve a decent amount, like table salt. Let's say you like salty water. Can you have infinitely salty water, or is there a limit there too? There is a limit there, because it turns out if you had 100 milliliters water, you know, probably the most salt you can get in there is about 37 grams. If you try to get more than 37 grams, it just isn't going to happen. Right? But 37 grams is a lot of salt. I mean, a lot of salt. So we say those are sugar, salt, those are highly soluble. Maybe not infinitely soluble. Is there something that's infinitely soluble?
Gold and mercury.
Yeah, gold and mercury. Or how about water and water? Is water infinitely soluble in water? Can you put any amount of water in water? Is there a limit? No, there's no limit. I mean, it sounds ridiculous because it's just water. You know? And so water and water mix perfectly. I mean, there's no limit to how much water you can put in water. But there are chemicals very similar to water. Some chemicals that are very similar to water are like methanol. Methanol is just like water. And so when you mix methanol and water, it's like mixing water and water. You can mix an infinite amount of methanol in water, as much as you want. You can put in so much methanol that pretty soon there's barely any water, and it's all methanol. So methanol, ethanol is the same way. Ethanol is infinitely soluble. Acetone is infinitely soluble. Those chemicals we call miscible. You know, that they're infinitely soluble. But as far as qualitative goes, it could just be anywhere from, you know, a little bit to a lot. We'd still call it soluble. Now, if we can't get that much in, we might call it slightly soluble. Slightly soluble. Slightly soluble, or we might call it insoluble. Insoluble just means a tiny bit will dissolve, maybe. So, for example, if you had a liter, you know, something like silver chloride, which we had up there earlier, silver chloride, a tiny bit, maybe a microgram will dissolve in a liter. You know, it's not 100% insoluble, but there's so little that actually dissolves for the most part. It's close enough. So these are very qualitative. We also have quantitative solubilities. And so we can always do this quantitatively. Like, say, for example, I want to know exactly how much I can dissolve. You know, how many sugar cubes max per cup of coffee? Well, I can measure it. You know, and weigh out how many grams that is. That's going to tell me how many grams of sugar I can dissolve in, let's say, a 250 milliliter cup of coffee. You know, that maximum, the process of measuring is what we call the solubility. So the max amount that will dissolve in a given amount of what we call solvent or liquid. Or water is defined as the solubility. So, for example, we could look these values up. They're usually given as part of the physical data. You know, and people will go out and measure these types of things. Just take a quick look.